Well, welcome back to our class on algorithms and data structures. Today, we're going to be getting into dictionaries. And so this will be following up to the information we had in our last very short lecture of some of the useful Java implementation. But we'll go ahead and get into this and go over how this works. So here is a listing of the textbook chapter contents, and we can be thinking about that as we do this introduction. If you need to check the meaning of a word, you look it up in a dictionary. If you need a friend's address, you consult your address book. If you need someone's telephone number, you check your list of contacts on your cell phone or search for it online. Each of these examples involves a kind of dictionary. This chapter describes and uses an abstract data type that generalizes our everyday notion of a dictionary. Subsequent chapters will examine implementations of the ADT. Previous examples, finding a word's definition, a friend's address, or someone's telephone number, are examples of searching a dictionary. Chapter 19 examined how to search an array, a chain of list nodes, and ultimately a list. You will see that a dictionary provides a more powerful way to organize searchable data than a list. So what about the specifications for the ADT dictionary? The ADT dictionary, also called a map table or associative array, contains entries that each have two parts. And so a keyword, usually called a search key, such as an English word or a person's name. A value such as a definition, an address, or a telephone number associated with the key. The search key enables you to locate the desired entry. So we have the figure that's embedded as part of this chart. It illustrates an everyday English dictionary. Each entry has a word as a search key, and the word's definition is the value associated with a key. In general, the search key and value in the ADT dictionary are objects as shown in figure 22. Each search key is paired with a corresponding value. So the ADT dictionary organizes and identifies entries by their search keys rather than by another criteria such as position. Thus, you can retrieve or remove an entry from a dictionary given only the entry's search key. The fact that every entry in a dictionary has a search key distinguishes the dictionary from other ADTs such as list, although you certainly could put an entry that has a search list in a list. A list data is organized by position, not by search key. Some dictionaries have distinct search keys, but others allow two or more entries to have the same search key. For example, a dictionary of students records organized by student identification number has distinct keys since those numbers are unique. On the other hand, an English language dictionary has duplicate search keys since it often has several meanings for a word. For example, my dictionary has 3 entries for book. One is a noun, one is a verb, and one is an adjective. So printed versions of a natural language dictionary, a telephone directory, a library catalog, and a thesaurus all have entries sorted by their search keys. These databases are dictionaries, but the ADT dictionary does not require assorted entries. Some dictionaries do sort their entries by search keys, while other dictionaries have unsorted entries. Why do our examples of printed dictionaries sort their entries? Because sorting makes it easier for the reader to find a particular entry. In contrast, you search a computerized thesaurus for a word, you would not be aware of the order of the entries, nor would you care as long as you could retrieve a particular entry. Thus, whether a dictionary has a sorted or unsorted search key is more of an implementation detail than a necessary characteristic of a dictionary. But remember that the details of an implementation affect the efficiency of the ADT operations in various ways. So the ADT dictionary has the same major operations: add, remove, retrieve, search, and traverse that are common to most database and other ADTs, even if a particular implementation sorts its entries or allows duplicate search keys. In particular, these operations are add a new entry to the dictionary given a key and associated value, remove the key, remove the entry associated with a given search key, retrieve the value associated with a given search key, see whether the dictionary contains a given search key, traverse all search keys in the dictionary, traverse all the values in the dictionary. In addition, the ADT dictionary has the following basic operations that are often included in the ADT: detect whether a dictionary is empty, get the number of entries in the dictionary, and remove all entries from the dictionary. So here is a listing of the Java interface for an ADT dictionary. So this specifies distinct key searches. The add method replaces the value associated with the search key that is already in the dictionary. Note that this method is not a void method as indicated in our initial specifications. Like the interfaces for the ADT list and sorted list, this interface specifies the data type of the entries generically. Since the search keys can have a data type that differs from the type of the associated values, we use two generic type parameters, K and V. K represents the data type of the search key, and V is the type of the associated values. So this is just a continuation for that listing. Well, let's now talk about iterators. The method get key iterator and get value iterator each return an iterator that conforms to the interface java.util.iterator that we discussed in the Java interlude 4. You can create iterators for the dictionary database that we instantiated in the previous segment by writing iterator string key iterator equals database.get key iterator. And then iterator student value iterator equals database.get value iterator. Recall that the iterator specifies a generic type in its definition. Here we have defined an iterator for the string search keys and another for the student values. These iterators traverse a dictionary's entries sequentially in the order in which they appear in the dictionary. You can use each of these iterators either separately or together, as we're showing in figure 23. That is, you can traverse all of the search keys in a dictionary without traversing the values using key iterator, all of the values without traversing the search keys using value iterator, all of the search keys and all of the values in the parallel using both key iterator and value iterator. In the last case, the search key returns by key iterator corresponds to the ith dictionary value returned by value iterator. Clearly, these two iterators have the same length since the number of search keys in a dictionary must be the same as the number of values. The dictionary loop displays either each entry in the dictionary as a key value pair. So keep that in mind. For a sorted dictionary, key iterator traverses the search keys in sorted order. For an unsorted dictionary, the traversal order is not specified. The examples in the text in the next section demonstrate these iterators in several contexts. You can use each of these iterators either separately or together, as we're seeing in the figure. So here we have, anyway, this is the first part, and this is the second part. So this is traversing a dictionary keys separately, and this is traversing a dictionary values, giving you a little bit more information there. Okay, that is in the textbook. You can review that more if you'd like. And so design and use of the class library of the class telephone directory. Our next step is to design a class to represent the telephone directory. A sorted dictionary will represent the data, which consists of name, number pairs. Each person's name can be an instance of the class name, and we first that we first encountered in Appendix B, and the telephone number can be a string without embedded blanks. Figure 24 shows a class diagram for our design. The class telephone directory contains an instant an instant phone book of a dictionary. The class has the method read file, which reads the data from the file and adds it to the phone book. It also has the method get phone number to retrieve a telephone number given a name. For simplicity, we are ignoring any other operation mentioned in the previous segment. So before we implement the class telephone directory, let's consider its use. A client would operate an instance of telephone directory and read the data file by invoking the method read file. The first two highlighted lines in the main method of listing 22 that we're showing here perform these steps. Given the name data.txt of the text file, main creates a scanner for the file and passes it to read file. Note the exception that might occur in creating the scanner. If you need more information about either exceptions or files, consult Java Interlude 2 and Supplement 2, which is online, respectively. After the file is read, main interacts with the user via the private method get name. Each name read from the user is passed to the method get phone number, where it will be the key in the search of the telephone directory. Notice how get names uses scanner to both read the user's input and then process it. This is just a continuation in that listing. And here's the third part, the fourth part, and finally the directory of telephone numbers, the testing output. So let's talk about the beginning, the implementation. The class telephone directory begins as shown in this listing 23. We assume that the class sorted dictionary implements a sorted version of the ADT dictionary having distinct search keys. A sorted dictionary requires its search keys to belong to a class that implements the interface comparable. And we assume that name does so. To implement the method implement the method read file, you need to know that the data file looks like. Suppose that each line in the file contains 3 strings, a first name, a last name, and a telephone number separated by blanks. That's a typical line might be the first name, Suzanne, Nouveau, and then a phone number, in this case, separated with dashes. So the method read file must read each of these strings. Recall that the main method in listing 22 in segment 20.8 creates a scanner for the file and passes it to read file. Using scanner's method next, read file can read each string in a line of data and assign them respectively to the variables first name, last name, and telephone number. Following Java statements, then we'll add the desired entry to the dictionary phone book. And so we have that listed here. And so using scanner's method has next and next, we extract each name and telephone number as strings from the text file. Then using the 2 statements we examined earlier, we create a name object and add it to the telephone number to the dictionary. Here's a method that searches. The class telephone directory has a method to find a person's telephone number. This method needs the person's name and the user must supply it. If we assume that the client will interact with the user and provide the desired name to the method, as does in the listing of 20-2, we could define a method for doing that. The method either returns a string that contains the desired telephone number or returns null if the number is not found. We could define a similar method instead of, in addition to the previous method. So additional methods to add or remove a person or to change a person's telephone number are straightforward and could be done as well. So let's talk about the frequency of words. Some words processors provide a count of the number of times each word occurs in a document. Create a class frequency count that provides this capacity. So that's what we're showing here, that this class is somewhat like the one in the previous example. So we will omit some of the design details. Basically, the class needs to count each occurrence of the word as it reads the document from a text file. It then needs to display the results. For example, if the text contains row, row, row your boat, desired output would be boat would be 1, row is 3, and your is 1. The class will have a constructor in the methods read file and display. As in the previous example, read file will read the input text from a file. Then display will write the output. Listing 20-4 that we're showing now shows a client of frequency counter. It is similar to the beginning of the client in the previous example. Is the ADT dictionary the right one to use for this problem? A word and its frequency of occurrence in the document form a pair that is suitable as an entry in a dictionary. If we want to know a given word's frequency, the word should be the key search. Also, the words in the dictionary must be distinct, and if they are sorted, we can display them in alphabetical order. Thus, a sorted dictionary with distinct search keys is an appropriate choice for this problem. As in the previous example, we assume sorted dictionary is such an implementation. The dictionary will be a data field of a new class frequency counter, which will begin much like the class telephone directory in the previous example. So let's call the dictionary for the example word table. Since the value portion of any dictionary entry is an object, we use the wrapper class integer to represent each frequency. Thus, our class can begin as shown in the listing here, 20-5. Here's just some more details, part 2, part 3, and this is in the textbook. You can look over or just pause and look at those parts of the listing in more detail. Okay, well, let's talk about creating the dictionary. Now let's look at the method read file, which creates the dictionary from the text file. We invoke this method as we did earlier in listing 20-4 of segment 20.12. That is, the client passes to read file a scanner object associated with the text file. The method then can process the text file by using the scanner method has next and next. In the same way, the read file processed the file in segment 20.10. After extracting the next word from the file, read file checks whether the word is in the dictionary. If it is not, we add it with an associated value of 1. That is, the word has occurred once so far. However, if the word is in the dictionary already, we retrieve the associated value, its count, increment it, and store it back into the dictionary. To avoid issues of case, read file can change all words it reads to lowercase. So this is the first slide for that. And in terms of delimiters, that the programming tip at the end of segment 20.10 mentions that by default scanner uses white space characters as delimiters, but as in the example given in 20.12, our data can contain punctuations, so those characters must also be delimiters. You can use a scanner method, use delimiter to specify the delimiters. You can represent them by using the notation shown in figure S16 of supplement 1 online. If you want to get more information about that, you can pass a string of the delimiters to use delimiter. The simplest way to specify white space and punctuation as delimiters is to use the notation W, since it represents any character other than a letter, digit, or underscore. We use delimiters arguments // W+. Remember that we must duplicate the backslash to distinguish the notation from an escape character. The plus sign means one or more occurrences of. Thus, the statement datafile.use delimiter // W+ sets the delimiter to one or more occurrences of punctuation, white space, and some other characters that are not that will not occur in our data. For displaying the dictionary, now that we have created the dictionary, we need to display the results. An iteration of the search key will produce the words in alphabetical order. The parallel iteration of the values provides their corresponding frequencies. The following method is a possible solution to this task. And so we're showing that in this figure. And then finally, for the Java class library, the interface map, the standard package Java util contains the interface map KV that is similar to our interface for the ADT dictionary. The following method headers are for a selection of methods in map that are like the ones you have seen in this chapter. We have, and we could also just note highlights where they differ from our methods. And we have some color coding there that you can reference. Notice the difference in names of the methods. Map uses the method names put, get, contain key, and size instead of our names add, get value, contain, and get size. Map also has additional methods, contain value, that finds out whether a dictionary contains a given value instead of our methods get key iterator and get value iterator that return iterators to a dictionary's key and values respectively. Map specifies the method key set, which returns a set of keys, and the method values, which returns a collection of values. The Java class library contains the interface set and collection, and each of these interfaces has a method iterator that returns an iterator to the values in the corresponding ADT. Duplicate search keys are not permitted in a dictionary that conforms to the map interface. Each key must correspond to only one value. Also, some of the map's methods use object as the data type of the search key, which we can use the more specific generic data type K. Okay, well, that's it for our lecture introducing dictionaries. Thank you very much.